The limit comparison test is a test for deciding whether or not a given series converges or diverges, and you do it by comparing it with a series that you do know whether it converges or diverges. So the actual way it works is you take the limit as n goes to infinity of the ratio of the terms. If that limit ends up being a number c that is finite and positive, in particular not zero, then these two series are going to either both converge or both diverge. They're going to behave in the same way. In order to use this comparison test, there are some conditions. The main condition is that the terms of the sequence need to be positive. At least they need to be eventually positive. We don't care what happens to, say, the first 3 terms, the first 4 terms. Eventually, though, these terms need to all be positive. In particular, the way that we actually use this most often is we use our comparison series Bn as either the P series or the geometric series, because we can easily determine when those two series converge or diverge. The P series converges whenever this value of P is greater than 1, and the geometric series converges when this value of R has an absolute value that's less than 1. So the basic idea behind this actual comparison test is that we're trying to decide whether the terms are decreasing fast enough towards 0 for the series to converge or not. So say we had 1 over n squared as our series Bn, those terms do decrease fast enough that that series converges. And if we had taken a ratio with an over bn, calculated this limit, and got a non-zero number, then that means that the series an has terms that are decreasing about as quickly as the bn's. And so they're going to have they're both going to converge in that case. So we'll look at a more specific example. We're going to try and decide whether this complicated looking series converges or diverges. And to do that, first we'll just say that this series is the one that we're calling an, and so it has terms of this form. And we're going to decide what these terms behave like when n is very large. We're going to do that by identifying the dominant terms in each of these parentheses. For example, when n is very large, 2n is going to completely dominate this minus 1, and this n squared, for example, is going to completely dominate this 3 when n is large. So basically, when n is large, the terms of this sequence are going to behave like the following, where I've just erased everything except for the dominant terms. And now I'm going to simplify this expression. Once you multiply everything in the numerator, you get 2n cubed. Multiply everything out in the denominator, you get n to the power 5, which simplifies to 2 over n squared. We could use 2 over n squared as bn, but it's a little bit simpler, in my opinion, to use 1 over n squared. So now we've identified an and bn. We're going to apply the limit comparison test, and we can do so because these terms are both positive. I guess for n equals 1, an is actually 0, but for all n greater than 1, they're positive. Now if you take the limit as n goes to infinity of the ratio of these two forms of the terms, we get the following expression. So let me just break down how I got this step. The an was just directly substituted in here, and instead of making a fraction of fractions, the way I divided by bn was by multiplying by its reciprocal. That makes the equation look a little bit nicer. So I've multiplied by n squared over 1, which is the same as dividing by 1 over n squared. We're interested in the behavior as n goes to infinity, but as we already discussed, an behaves like 2 over n squared when n is very large. So I'm going to replace this part of the limit with 2 over n squared. You could have done this step more formally by dividing the numerator and denominator by n cubed, and doing a couple more steps. This is what we end up with though, and the n squareds in the numerator and denominator will cancel, and the limit therefore is just going to be the limit of 2. The limit of 2 is 2, and that is a finite non-zero number. Since we have found that the limit is this finite non-zero number, happens to be 2, and we were comparing with a series that converges, the p series where p is equal to 2 converges because p is greater than 1, then the series that we were investigating also converges. Just one last note, I'm not saying that these two series are going to have the same value when you actually calculate their sum. All this test is saying is that they both converge.